In this mini lecture, we are going to talk about the ideal gas law. And if you've had chemistry, then you will have seen the ideal gas law. So hopefully this is a review for some of you. The pressure, volume, temperature, and amount of gas in a container are related to each other by what we call its equation of state. The simplest equation of state is the ideal gas law, where we assume that the gas is maintained at relatively low density and pressure. Things start to change a little bit when you have really high density and really high pressure. An ideal gas is what we define as a collection of atoms or molecules that move randomly and exert no long-range forces on each other. And each particle in an individual gas can be treated individually as being point-like, and they occupy the little masses on their own. The little particles on their own occupy a negligible volume of them by themselves. There are two ways we can define the ideal gas law, and one of them is by utilizing what we call the Boltzmann constant. And I just moved my picture so you can see the little picture of a mole. Okay, the moles will be important in a minute. The ideal gas law using Boltzmann's constant says that the pressure times volume equals this capital letter N times K, which is Boltzmann's constant, times T. Okay, so here P is the pressure, V is the volume of the gas, and N is the number of atoms or molecules in the gas. K is our Boltzmann constant, which is given here as 1.38 times 10 to the minus 23 joules per Kelvin. And T here is the temperature in Kelvin. Okay, so this N, the number of atoms or molecules in the gas. This is where moles come in. 1 mole of a substance is defined as containing an Avogadro's number of particles. Avogadro's number is 6.02 times 10 to the 23 particles per mole. That could be a molecule or an atom, whatever you have. Avogadro's number is 6.02 times 10 to the 23 of those per mole. A mole of any substance has a mass in grams equal to its molecular mass. And so you can find the molecular mass pretty much on any periodic table. So you just count all the protons and neutrons of the molecule or of the atom, and a mole of that substance will have a mass in grams equal to the total number of protons and neutrons per particle. And we can also define the ideal gas law by thinking about the number of moles. In this previous example of the ideal gas law using Boltzmann constant, we used capital letter N, which is the number of atoms or molecules in the gas. Okay, now we're going to use an expression for the ideal gas law where we use something else. Using moles, the number of moles of a gas, the ideal gas law states that PV equals little n times a new constant times R times the temperature. N is the number of moles of the gas. Remember that 1 mole has an Avogadro's number of particles. And R here is a new constant that we define as 8.31 joules per mole times Kelvin. So to find the number of moles in a substance, you take the total mass of that substance and you divide it by the molar mass. And the molar mass is defined as the mass of 1 mole of that substance, which is usually expressed in grams per mole. So the little n here is the number of moles, and the big N on the previous slide was the number of molecules in that gas. Now we're going to solve a problem where we make an application of the ideal gas law.
In this problem, we are going to combine the ideal gas law with Newton's second law. A beachcomber finds a corked bottle containing a message in a bottle. The air in the bottle is at atmospheric pressure, and it has a temperature of 30 degrees Celsius. The cork, that's this here, the cork, and this is the body of my bottle. The cork has a cross-sectional area of 2.3 centimeters squared. The beachcomber places the bottle over a fire, expecting that this increased pressure will push out the cork, and eventually it will. So, at a temperature of 99 degrees Celsius, the cork is ejected from the bottle. What was the pressure in the bottle just before the cork left it? Okay, so we're going to figure out what was the pressure inside the bottle when the gas inside the bottle reaches a temperature of 99 degrees Celsius. So in order to find this, we just have to use the ideal gas law. Okay, so just finding the pressure inside the bottle in order for the pressure to be strong enough that it's going to push out the cork from the end here. So we are going to play a little trick, which you can always do with the ideal gas law. So we know that the final pressure times the final volume of the gas inside the bottle has to equal nRT final, okay? But we also know that the initial pressure in the bottle times the initial volume has to equal nRT initial. Okay, so I always know that PV equals nRT. That always is the case. So I can always create these ratios like this, where I'm dividing PV equals nRT at some initial state by the ideal gas law for that gas at some final state. Okay, so I'm doing here. And we can always do that for any gas whenever we're using ideal gas law. You can always do this kind of ratio trick if you're given some initial quantities and you're trying to find some final quantity, or vice versa with the ideal gas law. Okay, so if I look here, I know that my volume is fixed. It's fixed to the shape of the container. So as I'm heating up and the pressure is changing, my volume is not changing. So if I divide, well, so V final on top is the same as V initial on the bottom. So those would cancel out with each other. And these two values are constants in R, so they would cancel with each other. So we're just left with P final over P initial equals T final over T initial. So I can solve this for P final, the pressure inside the tube, or the pressure inside the bottle, whenever we've heated it up to some final temperature. So that's going to equal our initial pressure times T final divided by T initial. We are going to assume that the pressure inside the bottle is at atmospheric pressure. That's what this says here. And we're going to use for atmospheric pressure 1.01 times 10 to the 5 pascals. And then we have to multiply it by T final over T initial. Okay, but for the ideal gas law, these temperatures always have to be in Kelvin. Okay, so how do I get these temperatures to Kelvin? You can always convert Celsius to Kelvin by adding 273. So if we take 30 plus 273, that'll give us our new initial temperature, 30 plus 273 Kelvin, and our final temperature will be 99 plus 273 Kelvin. Okay, so over here for my final temperature and my initial temperature, final I'll put 99 plus 273 Kelvin all over our initial temperature, which was 30 plus 273 Kelvin. Okay, and then I find that the pressure inside the bottle, once we've heated it up, is 1.24 times 10 to the 5 pascals. Then for part B, what force of friction held this cork in place? Well, let's see. We have a force from the pressure in the bottle pushing out on the cork, and then we have a force from the external pressure pushing in on the cork, and then we're going to have the force of friction. Okay, so if we draw kind of the free body diagram on this cork here. Okay. What I'm going to call the force from the pressure inside the bottle, that's going to be pointing in this direction. So I'm going to call this force in. So the force from the pressure inside the bottle wants to push on the cork this way. And then there's a force from the atmospheric pressure out here, and so I'm going to call this F out. That's the force from the pressure outside of the cork that wants to try to push it back in. Okay. And then we have the force of friction. Okay, we know that my cork is going to pop out this way. The force of friction opposes our impending direction of motion in this case. So the force of friction is going to be pointing opposite the direction of motion, so inward toward the center of our bottle. So we've got our three forces here. We're only going to think about the forces in the horizontal direction here. We can use Newton's second law in the horizontal direction. We've got the sum of our forces in the x direction equals mass times acceleration. There is no acceleration. This is just at the moment, just before the cork pops out of the bottle. So we are in equilibrium for the moment. We have the force from the pressure inside the bottle going to the right. So that's a positive force. So I'm going to call that Fn. And then we've got the force from the pressure, atmospheric pressure outside the bottle pushing this way. That's to the left. So that's a negative direction. So minus F out. Because remember, these forces are still vectors. And then we have the friction force opposing our direction of motion. And we just want to solve for the friction force. So the friction force is going to equal F in minus F out. All right. Remember, pressure is equal to force over area. So this force we can also write as pressure times area. So we can write this as P in times the area, cross-sectional area of the cork, minus P out times the cross-sectional area of the cork. Okay, so I'm going to factor out this area times P in minus P out. All right, and our cross-sectional area for our cork was 2.3 centimeters squared. Well, I've already got my pressure over here in pascals. So what I'm going to do, and that's an SI unit, we need to have this area, instead of in centimeters squared, we need to put it in meters squared. So how do I do that? Okay, well, let's see, 2.3 centimeters squared, we've got to get it to meters squared. So we have to multiply it by a conversion factor. How many centimeters squared are there in 1 meter squared? Well, let's see. So 1 meter squared, that's 1 meter times 1 meter, okay? Length times width, 1 meter times 1 meter. There's 100 centimeters in a meter, so that will be 100 centimeters times 100 centimeters. And so these go away, okay? 2.3, so that cancels, oh, those centimeters squared cancels with these down here. So we'll have 2.3 divided by 100 times 100 to give us this area in meters squared. So that area in meters squared is 2.3 times 10 to the minus 4 meters squared. All right, so over here, my area will be 2.4 times 10 to the minus 4 meters squared times the pressure inside the bottle, which we just found right here, 1.24 times 10 to the 5 pascals, minus the external pressure. We're going to assume the external pressure is at atmospheric pressure, the pressure out here outside the bottle. So minus 1.01 times 10 to the 5 pascals. And then that gives us a friction force of 5.29 newtons. A friction force of 5.29 newtons is acting in order to keep this cork from exploding out of the end of the bottle.
Before we leave gases, let's talk about the kinetic theory of gas. Let's think about gas molecules as being like billiard balls. And these billiard balls, these gas molecules, let's put them in a container. And those molecules are bumping around inside the container. They have some kinetic energy. Those particles, as they're bumping around inside the container, are exerting a force on the container. Think about impulse. Impulse was the change in momentum of a system. Okay, so these particles have some speed. They're bumping into the wall. Okay, you've got a change in momentum, and that's applying a force onto the wall. Since we're applying a force over some area, we're going to have a pressure. Then we can derive an expression, which I'm not going to walk through that derivation for you this time, where we can say that the pressure on the walls of that container times the volume inside that container of the gas equals 1/3 times big N, which is the number of molecules inside the container, times the mass of one molecule, times v squared. And then we have this little bar above it because this is the average speed squared of those molecules. Okay, and so PV is equal to 1/3 N M V squared, and PV we also know we can write it as little n RT or big N KT. We have this expression here that we just derived where we've got big N on both sides, which can cancel out on both sides. And then I could bring the 3 to the other side, so then I would have mv squared equals 3 KT. Okay, mv squared equals 3 KT. I can multiply both sides by 1/2. That gives me a kinetic energy, 1/2 mv squared. So if I do that, then I have 1/2 mv squared is equal to 3/2 KT. And where does this 1/3 come from? Students usually ask me about that. Where does that 1/3 come from? Well, you can look at actually your textbook has the derivation for this expression here. But this comes about because you have the velocity of your molecules actually has 3 dimensions. You've got the x dimension and the y dimension and the z dimension. And so this 3 here comes from the fact that we've got 3 dimensions of our velocity that's slamming in here to the edges of our container. So again, the average kinetic energy, or you can also think about the average kinetic energy as being the thermal energy of the system. The average kinetic energy of n number of molecules is equal to 1/2 mv squared is equal to 3/2 nkt. That's also equal to 3/2 little n, which is the number of moles, times our constant RT. We will introduce a new quantity that we call the RMS velocity of the molecules, or the root mean squared velocity of the molecules, which is just the square root of your average velocity squared. Okay, so that's the RMS speed of a gas. And then that will be then equal to square root of 3 KT over M. That's also equal to the square root of 3 RT over big M. So here, in this first expression, the little m is the mass of an atom, which is the molar mass of your gas divided by Avogadro's number. And big M over here is the molar mass in kilograms per mole. Now, not all of the particles inside a volume of gas are going to be moving at the same speed. That's why we just calculated this RMS, the root mean squared speed, kind of like the average speed of the molecules in a gas. Here we have what we call the Maxwell-Boltzmann distribution of speeds of molecules in an ideal gas. We've got the probability on the vertical axis that the molecule of the gas will take on that speed. And on the horizontal axis, we've got the velocity that that molecule of gas achieves, okay? And so this distribution here says that if we think about all the particles inside a volume of gas, this, if we counted up the speeds of all those little particles, this is what that distribution of speeds would look like. They do not all have the same speed, okay? There's a quantity that is here the most likely speed. That's the peak of this distribution here. The most probable speed for those particles to take on is sitting right here. Our RMS velocity, the average velocity that we saw, is right here. So the most likely speed for a molecule inside a gas is actually smaller than the average speed for a particle inside the gas. Why? This would not be the case if this distribution were symmetric around the peak here, but we see that it's not. Actually, we reach a peak here of the distribution, and then we have a long tail out here. So then if you take the average of all of these speeds, actually the average is going to be further along on this side. It'll actually be a larger value for our average because we've got this longer tail here. So there's actually a lot of particles over here that are going to take on a speed that's greater than our RMS speed, or that's greater than our most probable speed here. Now, this Maxwell-Boltzmann distribution is also dependent on the temperature, and the distribution is shifted to higher speeds and is broadened for higher temperatures of the gas. Here in red, we've got the Maxwell-Boltzmann distribution for a gas at some temperature. And then temperature 2, a higher temperature, is our green distribution. And we see that the most probable speed for the molecules inside a gas is actually shifted to higher speeds at larger temperature, but also our distribution becomes more symmetric around the most probable speed. So you're still going to have your RMS speed. It'll be a little bit larger than the most probable speed, but it won't be as different from the most probable speed as it is over here where our gas is at a lower temperature.